Assalamualaikum warahmatullahi wabarakatuh. My name is NAFISAH binti MUHAMAD. My metric number is 200355. Today I want to present the question number 5, which is the technique to study transition state structure of a reaction. The stereochemically unambiguous result of SN2 reactions, which is the complete inversion of configuration of the reaction center, proves that the transition state structure differs considerably from the SN1 reactions. According to the SN2 reaction schematics, the substrate, which is electrophile as well as the nucleophile, participate in the transition state. Obviously, the nucleophile takes the substrate from the opposite side of the leaving group as complete inversion takes place. In the transition state, the nucleophile carbon bond is partially cleaved, while the nucleophile carbon bond is partially formed, and the remaining three substituents are arranged trigonoplanar around the central carbon. The central carbon is sp2 hybridized, whereas the p orbital is used for the partial nucleophile and nucleophile carbon bond. As a result of the transition state structure, the movement of the remaining three substituents is comparable to an umbrella inversion in a windstorm. This inversion is called Walden inversion, named after Paul Walden. Drawing out the reaction, it looks a little like this, using nucleophile as a substitute for hydroxide ion and M as a substitute for sodium ion to make it more general. That's it. That's the transition state. Again, it is the point of highest energy which is most unstable, since we have two partial bonds at their maximum weakest length. Furthermore, the geometry has gone far from the ideal, which is tetrahedral, to one with more steady interactions, which is trigonal bipyramidal. So this is the formation of transition state in SN2 substituent reaction. Since this is a painful and unhappy situation for both molecules involved, the lifetime of the transition state is extremely short and rapidly reacts to the product. We have a name for this point, which is maximum peak. The difference between the energy of the starting material and the transition state is called the activation energy. So, given a diagram for the progress of reaction, we can figure out the activation energy by subtracting the energy of the transition state from the energy of the product. So this is the reaction energy diagram for simple substitution reaction SN2. A is the reactant, B is the transition state, and C is the products. So I will pass to my friend FARZANA. Thank you.
Assalamualaikum warahmatullahi wabarakatuh and a very good afternoon. My name is FARZANA binti AHMAD GHAZALI. My metric number is 200473. So now I will explain a little bit about the technique to study the transition state. So based on the transition state above, we can correlate it with a mountain pass model to study the reaction coordinate, free energy, and also the reaction entropy. So you can see from this diagram, there is a two-peak mountain here in which this mountain pass model will illustrate the energy of transition state and the entropy of a reaction. So each point of the mountain surface represent a specific atom spatial arrangement and energy of the system, in which from the diagram, it represent the each of the mountain surface, high energy region, the transition state region, and also the another high energy region here. So the starting products are located at the bottom of the mountain, while the products are located at the opposite side of the mountain, which is here. This is the starting products, which is the reactants, and the opposite bottom is the products. So in order for reactants to form the product, they have to form the transition state, which is an intermediate, consists of cleavage and formation of bond which occur at the same time. This is referring to the SN2 substitution reaction. So from the model, transition state of reaction is represented by the mountain pass, which is from the diagram is here, the mountain pass here, which is in the middle of the two mountain peak here. So this region require the least amount of energy, and the reaction coordinate is the direct connection of starting materials, transition state and products, which is based on the model illustrated by the red arrow. So this is the reaction coordinate. Okay, here the red arrow represent the reaction coordinate to illustrate the correlation between the reactants, transition state, and the products. So a mountain pass that is brought in cross direction represent a reaction with lower free Gibbs energy delta G plus, while a narrow mountain pass in cross direction represent a reaction with higher free Gibbs energy. So this is due to a broader mountain pass, more spatial arrangement of atoms with equal or nearly equal energy are available in or near the transition state. So, the entropy of the transition state delta S plus and the activation energy of the reaction are also higher. So that's all from me. Thank you.